our last topic for this section is outliers. And if you've ever gotten a definition for outliers before, please forget it right now. I'm telling you as a statistician that any like mathematical formulaic way of defining what an outlier is not good. And that we should really just be sticking with an intuitive sense of what an outlier is in order to really be able to understand what it is we're talking about. And what all an outlier really is a value that lies relatively further away from the other values in our data set. So if I've got things kind of clustered around right here, and then I've got some other value that's like way over here, that's an outlier. Okay, so it's going to be relative to how spread out our other data is. And this becomes a really complicated thing to talk about mathematically, and especially to talk about well. So let's just keep that intuitive graphical idea of what an outlier really is. It's something that's further away from the data than other data values are, right? Where generally speaking, they're kind of over here, and then I've got some other value that's over there. That's an outlier, okay? That's all we really need, all right? So here's how this relates back to the topic of this section, which is distribution shapes. It turns out with left skew distributions, we can expect our outliers to be low outliers. So let me go back to that left skew that we saw before, right? So I said it was left skewed because this shape extends further out to the left than it does to the right. So that's telling me that if I were to get some value that's far away from the other ones, because this tail extends out very far, if I'm seeing a value that lies far away from the other main values, it's going to be on the left. Okay, so this left skew implies that if we get any outliers, it's much more likely to be on the left. And what's on the left of the number line? Smaller numbers, right? Low outliers. Similarly, on these right skew distributions, we would expect to get high outliers for the same idea. I've got this tail extending further out on the right than it is on the left, so I can expect that I'm going to get these values much higher than these middle values. These will occur much more frequently on the right than they would on the left if they're going to be far away from the other values, right? That's what our intuitive understanding of outliers is supposed to mean, is that the outliers are going to lie far away from our typical values, okay? And if they're lying far away on a right skew distribution, I would expect them to be high values, right? Because that's where this tail extends out to, is toward higher values. So just know these kind of two facts here, that with left skew distributions, we can expect low outliers. With right skew distributions, we can expect high outliers. These ideas of left skew and right skew are directly tied to these outliers. Now, if I look at this, right, this histogram, right, the thing that we've been using to identify distribution shapes, I see that most of our values are between 40 and 99 here, with just this one thing right here that's between 10 and 19. And notice the separation, right? There's literally nothing in between. That's telling me that this is far away from the other values. And the way that I can tell you right now about how tied together this idea of skew and outliers are is imagine in your head, if this wasn't here, well, then it would look pretty close to symmetric, right? And so I don't want to throw out these outliers. They're immediately telling me, oh, I've got left skew here. I can expect to get unusually low values, right? All this information is incredibly useful. So outliers are not something, right, where in plain English, sometimes it sounds like outliers are like something to be dismissed. They're not important. Sometimes in statistics, they're one of the most important things because it's telling us which direction that skew is and where we can actually expect to see these unusual values.